Welcome to the Explainer. Look, today we're peeling back the layers on the architecture of modern AI. We're stripping away all that hype and getting straight down to the absolute physics of computation. If you've ever sat there wondering exactly how these massive models crunch mountains of data without literally melting the hardware, well, you are in the right place. We're diving into the Convolution Theorem, but we're not doing it like some 19th century mathematician. No, we're looking at this like AI engineers. We're going to examine the raw, gritty reality of modern GPU computing and see exactly what happens when elegant math collides head-on with silicon. And I want to start right here with this absolute truth. The convolution theorem isn't just a theorem, it's a computational shortcut. We are absolutely not here to debate pure theory today. We're here to expose the engineering realities behind AI. This theorem right here, it's the bridge that makes complex neural networks even possible. And knowing when to use it, and maybe more importantly, when to completely ignore it, is exactly what separates a novice from a master architect. So here's our blueprint for today. We'll start with the universal translator, then look at the sieve versus the recipe filter, hit a quick cross-correlation warning, dive into the hardware war, and wrap it all up with modern AI engineering. All right, let's jump straight into section 1, the universal translator, mapping the theoretical domains. You can really frame this whole problem as two parallel universes. In universe A, the spatial domain, we've got a sliding window. Just imagine dragging a tiny magnifying glass over a massive, massive image, literally pixel by pixel. It's super intuitive, right? But mathematically, it requires O of n times k operations. For huge signals, this is just agonizingly slow. But then we have universe B, the frequency domain. Over here, that extremely slow spatial sliding is mathematically identical to a virtually instantaneous element-wise multiplication. Thanks to the Fast Fourier Transform, or FFT, the time complexity drops drastically down to O of n log n. It essentially acts as this universal translator, turning a tedious sequential chore into a lightning-fast parallel operation. Moving right along to section 2, sieve versus recipe filter. Let's talk about the smoothie analogy. So let's actually visualize this. Imagine you're starting with some really muddy audio data, just completely filled with this annoying high-frequency hiss. Now, the spatial approach is kind of like pouring this muddy audio through a physical sieve, inspecting every single drop. Sure, it works, but man, it's tedious. But if we pass it through a Fourier transform instead, it acts like a prism. It instantly breaks that muddy audio down into a recipe of frequency bars. You know, like 50% bass, 30% vocals, and 20% high-frequency hiss. From here on out, our filter is no longer this clunky physical sieve. It's just a rule. We can apply a low-pass filter by literally just crossing out the high-frequency bars on our recipe. It's almost like a chemical reaction. We're just instantly deleting the bad ingredients, element by element, and mixing it back together. The final output is exactly the same, but the process itself, fundamentally superior when you're dealing with massive datasets. Which brings us to section 3, the cross-correlation warning. Textbooks versus PyTorch code. I really want to point out a massive discrepancy here between what you read in academic textbooks and what actually happens in practical code. Consider this a critical warning. In pure mathematics, a discrete convolution absolutely mandates that the kernel, meaning your filter, must be flipped backwards before you slide it across your signal. You'll see this represented by the n minus k in the equation. The theorem literally only works mathematically if you flip the kernel first, and that's just due to the way complex exponentials behave in the frequency domain. But, and this is a massive but, deep learning frameworks absolutely do not do this. So the really crucial takeaway here is that when you call nn.convolution2d in PyTorch, technically speaking, you aren't actually doing a convolution. You're doing cross-correlation. If you look at the cross-correlation equation, it's n plus k. There's no minus sign. The kernel isn't flipped at all. So why do we intentionally break this strict foundational mathematical theorem? Because in AI, we aren't handcrafting our filters anymore. The neural network is learning them on its own via backpropagation. If we actually force the GPU to flip a kernel, the network would just learn the exact opposite weights to unflip it anyway. It's totally useless computational overhead. We're basically sacrificing pure mathematical fidelity for raw engineering efficiency. All right, section 4, the hardware war. Spatial M to col versus frequency FFT. Because as we just saw, mathematics isn't the problem here. The hardware is. Now, you might think GPUs actually use that sliding window technique we talked about earlier. Well, they don't. Doing sequential memory access absolutely destroys GPU performance. Instead, AI engineers use something called the I'm-to-call trick, or image-to-column. The GPU basically forcefully unrolls patches of your input image into this massive 2D matrix. Then it reshapes your kernel into a row vector. Finally, it executes a massive general matrix multiplication, or GEM. I mean, this is incredibly brute force, so why on earth do we do it? Because modern GPUs are absolutely packed with tensor cores that are specifically designed to obliterate dense matrix multiplications at absolutely terrifying speeds. Let's put this into perspective. Imagine a dual speedometer for your GPU. On one side, we have the spatial method, utilizing that M2-call matrix trick. On the other, we have the elegant frequency method using the FFT. If we set the kernel size, K, to a tiny 3 by 3, which is the standard for convolutional neural networks like ResNet, just look at the speeds. The spatial matrix method is completely redlining at maximum speed, while the FFT approach is practically crawling. For small kernels, the raw, unadulterated brute force of tensor cores doing matrix math completely overwhelms the elegant O of NlogN complexity of the FFT. But watch exactly what happens when we change the environment. If we dial the kernel size all the way up to 65,536, which is the kind of massive context window used in modern sequence modeling, our speedometers completely flip. That spatial I'm2call method, it hit zero speed. In fact, it just threw an out-of-memory error, because unrolling a kernel of that size requires literally terabytes of RAM. But look at the FFT now. It's absolutely dominating. Because the FFT's complexity scales logarithmically, totally independent of the kernel size, it is the absolute victor here. And that right there is the real engineering reality. There is no single best algorithm. It is entirely dictated by your hardware context and the sheer scale of your architecture. Let's bring this all together in Section 5, Modern AI Engineering, and look at where this theorem actually appears in AI. This spectrum of design choices really reveals everything about how models are built today. At one end, standard CNNs like ResNet strictly stick to spatial 3 by 3 kernels just to keep feeding those hungry tensor cores. But then look at MobileNet. To get AI running smoothly on your smartphone, engineers exploit the theorem's algebra to actually factorize the convolution into depthwise and pointwise steps. That gives them an 8 to 9 times reduction in mathematical operations. Huge deal. Then you have WaveNet, used in audio generation, which uses dilated convolutions, essentially poking tiny holes in the kernel so it can see further out without having to do extra math. And finally, on the other end, modern LLM alternatives like Hyena abandon the spatial world entirely. They rely purely on the frequency FFT to process massive sequence lengths that would instantly choke a standard transformer model. But building these structures definitely comes with some severe failure modes. For instance, if you're generating text or audio token by token, like in an autoregressive model, you absolutely cannot use a standard spatial filter. Think about it. A standard sliding window looks both left and right. If you do this during training, your model will implicitly cheat by peeking at future tokens. Sure, you'll get a perfect training loss, but it'll output total gibberish in production. To fix this, you have to architect a causal convolution using asymmetric left padding, ensuring the model is strictly blind to the future. It's one of those critical engineering details that pure math simply doesn't warn you about. So we've seen how elegant mathematics has to bend to the sheer brute force of GPU hardware, and how the convolution theorem acts as this incredible universal translator, giving us a massive computational shortcut. But here is the question I want to leave you with today. As the demand for these massive sequence lengths in AI continues to explode, and spatial matrix multiplication hits a very hard silicon wall, are we looking at a future where all foundational AI models operate purely in the frequency domain? It's a pretty fascinating structural shift to think about. Thanks for joining me for this explainer. Keep questioning the architecture.